All right, now we'll write down the analytical solution to the cascading tank filling problem. So first I'll remind you what the equations are. d by dt of h1 and h2. And the way to solve this is to realize that the water level in tank 1 doesn't depend on the water level in tank 2. So in fact, tank 1 is uncoupled from tank 2, and so we can solve the solution to that problem using the same methods we already have. And the equation for the water level in tank 1 is just d by dt. This equation, and this is the same equation we've already solved using the integrating factor method, so I can simply just write down the solution. This solution is given by this forcing and involve this timescale tau 1, which appeared here. Now, if we know h1, then h2 is now also of this form, but where the forcing now it depends on the water level in tank 1. So let's write down the equation for what's going on in tank 2. So this equation is of the same form as the one for tank 1. The only difference is that the forcing now is expressed in terms of the solution for the problem in tank 1. But this is now a known function. It's just this one. So it's now straightforward to write down the solution for tank 2. It'll be of the same form as this one, with the forcing replaced by this. We could, in principle, replace h1 by this expression. If we did that, we'd have to be careful to change everywhere we see everywhere we see a t here with a t prime. This is t primed. Right? We're integrating over the forcing. So h1 over tau 2 is the analog of r over a1, and it's integral over t prime. So here I need a t prime. But if we were to substitute this in here, we'd have to be careful to first replace everywhere we see here with a t, here and here, and here with the t primed. But that would conflict with the existing t prime in the expression, so we'd have to change this one maybe to a t double prime. So maybe I'll write this down to make sure it's clear what the integrals mean. So I'll recopy this answer, but now replace this with the solution. So h2. And now I'm going to put in this expression for what h1 of t prime is. So that will be e to the minus t primed t naught over tau 1. So this t is a t primed. This t up here becomes a t primed. So the first t becomes a t primed, the second t becomes a t double primed. Tau 1 r1 of t double primed dt double primed. And then I can close this bracket. And then the integral here is with respect to dt primed. And so this would be the full solution. Now, written out in this way as two nested integrals, it's hard to see what the solution looks like. So what I will do is I will take this one and express it in MATLAB to see what it would be. All right, to evaluate the analytic expression, on the computer, we have to be able to do this integral. This integral, it turns out, can be done analytically for the particular source function I've done, but you can try it out, but the expressions are quite messy. And especially when we take the solution from H1 and we stick it in here and we do this integral analytically, we get something that's very messy. And so it turns out that I think it's going to be easier to do a semi-analytical evaluation of this function by evaluating these integrals numerically, by discretizing the integrand and doing a sum. And so before I go ahead and do this, I want to do a brief aside back to numerical methods, and I want to compare the order of convergence of three ways to do the integrals: Euler forward, Euler backwards, and Trapezoid Rule. And so it's kind of funny that I backtrack here when I try to do the analytical integration. And the reason I want to do this is because the numerical integration of this integral turns out to be quite sensitive to the resolution at which you do it. And that's because the integrand is falling off exponentially, and if you don't have enough points, you get a poor answer. And so it's useful now to have a good integration scheme to do this convolution integral, and this one also. So let's do an aside on numerical integration, and I've talked about this a little bit before, but we're going to want to do it a little bit more carefully this time. Okay, so I have a function this would be x over here, and this is f of x, and suppose my function is, I don't know, something like this, and we want to find the area under the curve between the two endpoints from here to here, and we're going to discretize it. So just for the purpose of this, I'm going to divide it up into two. So this will be x1, x2, and x3. And if we do the Euler forward approximation, we will evaluate this using rectangles. So evaluating the function at the left of the interval, taking a rectangle, and this one is kind of boring. The rectangle has zero area, and then doing it for the next panel, evaluating this, and then computing the area of this rectangle. So the Euler forward is going to approximate the integral from x1 to x3 of f of x dx as the area of these two rectangles. So it'll be f, the height, f at x1, times the width, which is x2 minus x1. That's the area for the first panel, plus f at x2, the height of this rectangle, times its width, x3 minus x2. Now, the Euler backwards is going to be similar, except we're going to go the other direction. We're going to go from evaluate the function here at the end of the interval, and then take a rectangle. So it'll be this one, and then this one. So Euler backward and f at x2 times, this will be the height, and the width is the same, x2 minus x1, plus the height f at x3 times x3 minus x2. And then finally, for the trapezoid rule, we will take the area of the trapezoid over here, this one. So the trapezoid rule is the following: trapezoid approximates x1 to x2. And it's nice I use a gold color because it's going to be much better than these two. F of x dx is going to be approximated as f. So the height, so for the area of the trapezoid, the formula is you take the average of the heights and multiply by the base. So this will be f of x1 plus f of x2 divided by 2, that's the height, times the width, x2 minus x1, plus f of x2 plus f of x3 divided by 2 times x3 minus x2. So these would be three formulas for evaluating the area under the black curve by discretizing it in terms of just 3 points. So in the example we're going to do on the computer, we're going to first pick a particular function and evaluate this, but progressively increasing the number of points from just 2 points, 4 points, and then 8 points and 16 points and so on, every time doubling the number of points, and look at how quickly the integrand approaches the true value. So the function I'm going to pick is going to be the integral from 0 to 2 pi of x cubed dx. And that's easy to evaluate. It's going to be 2 pi to the power 4 divided by 4. And so this is the exact answer, and then we're going to approximate it from these 3 points of view. So let's make our test function our exact 2 times pi to the 4th divided by 4. And now we're going to make my 3 integration rules. Function r is Euler forward t and f and so if I pass in only 1 point, then the way I'll write the function is that it's going to compute the area between the first and the last value of t. And it's assuming that f has been evaluated at the discrete t points. So if I pass in only 1 point, then the first and the last point are the same, and then the area is 0 because there is no width. But on the other hand, if the length of t is bigger than 1, then I'm going to have at least 2 points, and I could take I want to find the area between the first and the last point. And I'm assuming that f and t have been evaluated in a consistent way. R is going to be equal to, so for the Euler forward, I'm going to evaluate the function at the left of all the endpoints. So that's going to be f at 1 through n minus 1. So I'm going to use the first, the second, all the way up to, but I'm going to skip the last point. And I'm going to multiply that by the width of all the points. So that'll be t 2 to n minus t 1 through n minus 1. So this is all the widths of all the panels. And then I return that as my Euler forward. The Euler backwards will be very similar. But now I'm going to evaluate at the rights of all the endpoints from 2 to n. And this one I will evaluate at the average of the first and last point of each panel. So over here, this will be 0.5 times plus f of 2 to n, like that. And of course I have to do the sums, right? They're all integrals. So here I should sum all this, and here also. And finally the last one. And now I'm going to try, in this little test script, I'm going to evaluate, progressively increase the number of mesh points. So hopefully these don't have any bugs. Let me put semicolons on these. All right, so the points I'm going to pick are going to be 4, k is equal to 2 up to 12, n is equal to 2 to the power of k. So the first time 2 points, because, oh, I need to start at 1. Yeah, so the first time k is 1, n is 2, the second time k is 2, n is 4, then k is 3, n is 8, and so on. And then I define my points. T is equal to lin space from 0 to 2 pi by n. So I'll define n t points. Now I want to evaluate my function at those discrete t points. So f is going to be t cubed. That's the function I'm integrating, the cubic function. And then I'm going to compute the error for each method of integration. So E1 of k is going to be the absolute value of the Euler forward minus the exact. And then E2 will be absolute value of Euler backward and E3 will be the error for the trapezoid rule. And I think, what did I call it? Oh, I didn't change the name. And then we want to make the plot of the error, and I'm going to plot it on a logarithmic scale graph. So semi log y E1, and E1 I will do it in red. Hold on, semi log y E2 in green. Hold on, and I wish I had a gold color for the trapezoid rule, but semi log y E3, and I'll put it in blue because I don't have gold, or I don't know what the code is for gold. Let's do a grid on, make the font size big. So what I'm going to plot is log base 2 of the number of points for the discretization on the x-axis, and on the y-axis will be the error. The absolute value of the error. Let's run it and make sure I don't have too many bugs before I get too far ahead of myself. Oh, it worked the first time. Unusual. Okay, so you can see here the error as a function of the log of the number of points is decreasing linearly on this log graph for both the trapezoid and for the Euler forward and Euler backwards, but you notice that the error is dropping much more dramatically for the trapezoid rule, which is the one in blue here. And in fact, this one is dropping quadratically while these ones are dropping linearly. And the best way to see this on the graph is to plot something which is decreasing linearly and something which is decreasing quadratically on the log graph to make sure that, as guide for your eye to read it off. So I'm going to add these curves. So let me add the guidelines. Semi log y, linear, and big dashed, and I'll do this one in red, and semi log y quadratic in blue. And I guess what I should do is define linear. So linear is going to be my points, my mesh points, are given as 2 to the 1 to 12, so 2 to the 1 through 12, and then this I'm going to raise to the power of -1. So it will decrease like this to the -1. And for the quadratic, it will be, the exponent will be -2. And let's do the test. Right, so here we have the two guidelines, and you can see that the linear decrease, the one that where the exponent is -1, is parallel to the error for the Euler forward and Euler backwards, whereas the one where the quadratic decrease is parallel to the decrease for the trapezoid rule. Alright, so that completes my brief aside on the convergence rate of the Euler forward, Euler backwards, and trapezoid rule. So now when we go back to this integral, we're going to use the trapezoid rule to evaluate this integrand. Okay, so where were we? Let's go back to our example 4. So we have our initial conditions, our taus, our forcing function, and now we want to do evaluate H1 at a discrete set of points, and we need to do this integral, discretized version of this integral. And we're going to use the trapezoid rule. So the first thing is to define the function, the trapezoid integration function. So I'm going to pick that one off from my little test script. Test.m. And then move this down here. Alright, so I have my trapezoid rule integration. Then I need to find a discrete set of points at which to evaluate the integrand. So let's discretize time, t. We'll go from linspace from 0 to t using endpoints. And I think I picked t to be 50 in the last example for the time stepping method, Euler forward, Euler backwards, and trapezoid. And I'm going to use, let's say, 100 points. Now I'm going to evaluate the integrand at those discrete points. So here I have s is the function. The value of s at the discrete time, I'm going to call that st. So s evaluated at t is going to be s of t. So to be clear what's going on, s is just a function. It's not evaluated anywhere. But s of t is going to be a discrete set of numbers, a vector of numbers, which correspond to the value of s evaluated at the discrete t points. So s is going to be a vector with as many points as t. Maybe I can just run it and show you what the difference is. So example 4. Oops. Linspace, there's no e. Example 4. And now t is a bunch of numbers, the length of t, the length of st, right? St is a bunch of numbers, but s is a function. Okay, I hope that's clear. And now we want to do the integral. So we're going to evaluate h1. So for I equals 1 through n, h1 of I is going to be equal to the first part, which propagates the initial condition, exponential minus t sub I minus t1. t1 is the same as t naught. Divided by tau 1 multiplied by the initial condition h1 0 plus then the integral, and for that we're going to use the trapezoid rule. We're going to put the t values that we want to integrate over. So we want to integrate from t from 1 up to I. only, right? We're going to, the first time through, we want to go up to point I, which is t sub I. And then the integrand, which is what we've already evaluated, but st. st from 1 through I, like that. Oh, st, but then I need to multiply by the exponential term. Exponential of minus t I minus t 1 through I. Whoops, 1 through I. Dot star. Let's see, I'm missing a parenthesis here. Parenthesis, parenthesis, that's good. And S. And the trapezoid rule. Then my semicolon. End. Alright, and this will give me the value of H1 at the 100 points between 0 and 50. And then I can do, if I know H1, I can now do this integral. So let's do that one. For I equals 1 through n, H2 of I notice this time I used tau 2 for the time scale. Multiply by H20, the initial condition for the water level in the second tank, plus dot 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 trapezoid rule T1 through I exponential minus Ti minus T1 through I. Oh, I just noticed an error here. I didn't divide through by tau 1. Tau 1. Yep. Tau 2. Right, there's these tau 2s and tau 1s in the form of the solution. Dot star, and what used to be st, the value of s, which was r1 over a1, which was r over a1, now I want h1 over tau 2. So this will be h1 from 1 through I divided by tau 2. Alright, let's check for bugs. Clear all. Example 4. Okay, so far no bugs. No obvious bugs. And now let's make the plots. So for this one I'll pick blue for the upper tank. Hold on. Grid on. Plot TH2 in red. And then I can do my labels. X label. Time in seconds. Y label. Height in meters. So let's run it, see what I get. Example 4. Okay, so this is my semi-analytic answer in which I evaluated the integrals numerically using the trapezoid rule. And I guess maybe I should compare this to the answer I got using the Euler forward and Euler backward methods. So for that, I'm going to close this figure or clear this figure. Example 2, I think is what I called it. Yes. Here is example 2. Let me make it a little bit bigger. And now if I run example 4, it'll plot my example 4 solution on top of this one. So example 4. And you can see it's not so good. And that's because I only have 100 points. If I picked more points, so if I now go up here and I pick 500 points, then the quadratic convergence of the trapezoid rule to do the integrals will decrease the error substantially. Example 4. And now they lie on top of the previous one. So let me clear the figure. Example 2 and then example 4. And now you can barely see the difference. And this time I used only 500 point. Let's see what I had used for the fully numerical method. Example 2.m, I had, how many points did we have? And 500, so they're the same, so roughly the same number of points. But if I do the integrals using the other integration rules, we'll see the error is the error is quite big. So let me go back to example 4.m and then add my other integration rules from the test.m. These ones. And now I can change to Euler forward and see how this does. And now the error is terrible, right? So these convolution integrals are quite sensitive to the integration rule. Let's test the Euler backward one. And it's wrong on the other way, but the trapezoid rule seems to do quite well. All right, so this concludes the lecture on solving the cascading tank problem.